Imagine you have an unknown substance. You're not sure what it is. You know it's not dangerous, but as a chemist, you really need to figure out at least its empirical formula, if not its molecular formula. Well, thanks to an infrared spectrometer, you know the elements that exist in that substance, but no other information. What can you possibly do? This is where combustion analysis comes into play. We're going to burn the substance in a furnace, see what we get, work backwards to figure out the empirical formula. So here's our furnace. This is where we're going to place our sample and cook it. You can see this is fire down here. It's supposed to be fire. Definitely fire. So our sample is going to go in here. And by definition, if we're going to combust something, we need oxygen. And we're going to go ahead and say that we've got unlimited oxygen. That unlimited oxygen is important. We can't have that be any sort of limiting reactant in our equation. Well, we're going to send this sample through the furnace, and we're going to gather the products. We have two additional parts to this machine. We have an H2O absorber, and then we have another compartment, which is going to be our carbon dioxide absorber. So we are assuming that the substances we're combusting have hydrogen and carbon. Sometimes there can be some other things as well, but for this example and for the AP exam, you only need to worry about 3 different types of elements. So our products make their way through, and we have some initial data. Our initial data is the mass of the original sample that contains all of our ingredients. The H2O absorber is going to tell us the mass of water that is collected on the product side. And then our carbon dioxide absorber is going to do the same thing for the mass of CO2. Now here is the most important part. We know that all of the hydrogen that was in the original sample needs to be yielded through water. So all that water that was given off, taken in by the H2O absorber, must have all of the hydrogen. Same with the carbon over on the CO2 side. So all the carbon is going to be taken in by that CO2 absorber. So that brings us to our example. We're going to combust our unknown. We've got a certain amount of the unknown at the beginning, in this case 2.04 grams, and we know it contains carbon, hydrogen, and oxygen. After the combustion, our absorbers tell us that we've got 4.49 grams of carbon dioxide and 2.45 grams of the water. Now all the carbon that was in that original substance has to be in that 4.49 grams of carbon dioxide. But we know there was unlimited oxygen that could have been added, so we need to account for that. Likewise, all the hydrogen is going to be found in that 2.45 grams of water. How do we get the empirical formula? Stoichiometry is our tool here. We're going to use stoichiometry to process this information. Working backwards from carbon dioxide and water, we're going to find out how much carbon and hydrogen in mass was found in that original substance. Then we can find the moles. Oh, actually, hold on. We're still going to need to find the oxygen mass that was added. But we can do that easy enough because we know the original mass of the original unknown compound. And now we know the mass of carbon and hydrogen. Everything else must have been from oxygen. Then we can find moles of all 3 elements. And once we've got the moles, we just find the empirical formula using the same procedure that we have in previous problems. So let's look at the stoichiometry. We'll do this quickly. 4.49 grams of carbon dioxide. Convert that to moles of CO2. And now we know we have 1 carbon atom per every 1 carbon dioxide molecule. Therefore, we have 1 mole of carbon per 1 mole of carbon dioxide. You can take a look here, make sure dimensional analysis makes sense. For the hydrogen, we take the mass of water, convert it to moles of water, and now we've got 2 moles of hydrogen per every 1 mole of the water. Convert that into mass of hydrogen, and there we go. We're sitting with 1.22 grams of carbon and 0.27 grams of hydrogen. Now how about the oxygen? We know that the total sample at the beginning contains the mass of the carbon and the hydrogen. Well, we just figured that out. All the remaining mass must be from the oxygen. So, little subtraction tells us that we have 0.55 grams of oxygen. Those three total should sum up to the total mass of our original unknown sample. Now that we've got a mass of each element, we can just calculate the empirical formula. How do we do that? Remember, convert to moles for each substance, for each element, find the lowest mole ratio, and go from there. Here's the answer. Our unknown sample has an empirical formula of C3H8O1. Now, if we used a mass spectrometer or some other instrument to find the molar mass of the substance, we could then also calculate the molecular formula.